Swayam Prabha. Digital India. Educated India.
So today we are in our 13th lecture and we shall be discussing the duality concept in linear programming. Now, first of all, let us begin with a product mix problem. What we shall do, we shall try to explain the concept of duality with the help of a problem, right? Uh, Let us see a problem, see its formulation and its solution, and understand that problem very clearly. And with respect to that problem, we shall explain duality, and then the theory and the concept part that also we shall explain thereafter. So here is a product mix problem. This problem we have taken up earlier also, but a very quick recap. There are two products. Three resources are required to produce the products. The resource availabilities are 360, 160 and 300 respectively. The first product requires 4, 2 and 2 units of resources for producing 1 unit. The second product requires 3, 1 and 3 units of the resource for producing 1 unit. If the profit coefficients of the two products are 600 and 400 respectively, find out how many of the two products are to be produced so as to maximize profit. So this is a very clear-cut, maximization problem, and the objective function is maximize z equal to 600 x1 plus 400 x2, where x1 is the number of product 1 to be produced and x2 is the number of product 2 to be produced. And these are the constraints with regard to resource 1, resource 2 and resource 3. That is 4x1 plus 3x2 less than equal to 360, 2x1 plus x2 less than equal to 160, and 2x1 plus 3x2 less than equal to 300. And there are the non-negativity constraints. So a very quick graphic solution to the problem will be like this. So these are the equality represented by the lines. 2x1 plus x2 equal to 160 is one such line between the point G and point D. 4x1 plus 3x2 is the second such line, that is between point E and point F. And 2x1 plus 3x2 equal to 300 is the third line between point A and point I. Now the solution space should be, because all the constraints are less than equal to, that means they are all towards 0, 0. So you see, what should be our solution space? Is it feasible? And what is the nature of the solution space? It is clear that for all the lines, the inequality represents the side towards the origin. All right, for all the three constraint lines. And what is the common area between all of them? That should be OA, B, C, D. That means the solution space should be OA, B, C, D. And all the 5 points are also, their coordinates are available. That is 0, 0, 0, 100, 30, 80, 60, 40 and 80, 0. So it is very clear that that is the solution space. It's a feasible solution space and it is also a bounded solution space. So therefore the problem is very clear cut. The basic feasible solutions are all known, which are equivalent to the corner point feasible solutions, nothing but O, A, B, C and D. So we have to evaluate the objective function in those 5 points, and the best of these points, the result, the best value of Z that is returned, that should be our optimal solution. So here is that evaluation. At point O, it is 0, Z value. Point A, it is 40,000. Point B, 50,000. Point C, 52,000. And point D, 48,000. So the optimal solution is point C, which is x1 star equal to 60 and x2 star equal to 40 and z star equal to 52,000. So the solution is known. Now let us talk about another view of the same problem. Look here, in the original problem, we are producing two products with the help of three different resources. Now, for the time being, let us say that we are not going to produce anything, but we have those three resources available with us. And let us say that these resources are renewable resources, something like, say, manpower. So you see, people we already have available, or maybe some maintenance facilities, some machining facilities. So all these resources, if you give to the rent in the market, then you may not be producing any product and you will be getting some rent. So let us say that those rent values are Y1, Y2, and Y3 respectively for the three resources. Is it all right? So if Y1 is the rent per unit for resource 1, Y2 is that for resource 2, and Y3 is that for the resource. What is the total rent that you are going to get? The total rent that we are going to get is 360 Y1 plus 160 Y2 plus 300 Y3. Now you see, if we try to make as much rent that the profit that we are getting, then you have to ensure that uh, the resource that was required for producing 1 unit of product 1 and the profit that you are getting for 1 unit of product 1, they should match. That means you should get at least that much rent, which is equivalent to the profit that we are getting for product 1. So what exactly we are saying is that by utilizing the resources, we should get rent of at least 600 from 4, 2 and 2 units of resources for the first product, and at least 400 from 3, 1 and 3 units of the resources for the second product. Let's go back and let us see the formulation of the problem. So look, here is the formulation of the problem. So in this formulation, what we are basically saying that instead of making the two products, that is X1 number and X2 number, if we give these three resources whose availabilities are 360, 160 and 300 respectively, the total rent that we are going to get is 360 Y1 plus 160 Y2 plus 300 Y3. That is the first thing. Assuming that Y1, Y2 and Y3 are the three rents. But then, we are not producing any product, we are getting the rent. So we should ensure that the amount of rent that we are getting, our original product mix business, because we are not doing it anymore, that should not be hurt. That means, the amount of profit that we are making, we should ensure that we are getting at least that much. So what we should do? So therefore, you see that 4, 2 and 2, these are the three resources that are required to make 1 unit of resource product 1. So how much rent we are going to get for 4 units of resource 1, 2 units of resource 2 and 2 units of resource 3? It is 4Y1 plus 2Y2 plus 2Y3. Now that is the total rent. And what was the profit coming earlier from making 1 unit of product 1? That was 600, because that was the profit coefficient. So that means the rent that you are getting, that is 4Y1 plus 2Y2 and 2Y3, the total should be greater than equal to 600. So that is the first observation. Now let us see the product 2. Now you think and tell me what should be the similar such thing for product 2, right? To make 1 unit of product 2, we need 3 units of resource 1, 1 unit of resource 2, and 3 units of resource 3. That means, total rent that we shall be getting equivalent to 1 unit of product 2 would be 3y1 plus 1y2 plus 3y3. And what was the profit for 1 unit of x2? It was 400. So that means the rent that we are getting for making 1 unit, instead of making 1 unit of product 2, rather giving the resources on the rent, we know that our rent should be 3y1 plus 1y2 plus 3y3 should be greater than equal to 400. All right, so this is precisely what has been shown here, that constraints for rent for each product should be then, by utilizing the resources, we should get rent of at least 600 and 400 for the two products, and therefore, for each unit of product 1, we should get those two constraints, 4y1 plus 2y2 plus 2y3 greater than equal to 600, and 3y1 plus y2 plus 3y3 greater than equal to 400. Now, you see, ideally, should you maximize the rent or minimize the rent? Obviously, we should like to maximize the rent. But if you maximize the rent and also take these kind of constraints, we are going to get a problem definitely, but that problem will be a different problem than the ordinary, our original primal problem. That was the problem that we have taken, which we shall call primal, just a little later. So you can understand that if we want an equivalent problem, that means we make at least that much profit so that the two problems are equivalent. That means we don't lose anything. So at the first, we must understand the floor. What is the minimum rent that we must get to make our business of renting our resources meaningful instead of making the product? Then instead of maximizing, we should minimize. See, original problem was maximizing profit given that certain resource constraints. Now we are giving those resources on rent, and we are ensuring through the constraints that at least that much profit is there. So what is the minimum such rent that we should get? If you take that kind of a formulation, then easily we can say that this formulation is going to be an equivalent problem. So what is that formulation? Minimize y equal to 360y1 plus 160y2 plus 300y3 subject to 4y1 plus 2y2 plus 2y3 greater than equal to 600, and 3y1 plus y2 plus 3y3 should be greater than equal to 400 for product 1, and this is for product 2, and y1 greater than equal to 0, y2 greater than equal to 0, and y3, which is not written, should be also greater than equal to 0. Now, why these y1, y2, y3 should fulfill the non-negativity criteria? Because look here, they are all rents. So rents cannot be negative. So obviously they are physical quantities. So they should be also greater than equal to 0. Right. Now let us look at it from another point of view. There is a principle which is known as the max-min principle. What is max-min principle? The two problems, that is the product mix problem and the rent problem, will be equivalent if we minimize the total rent obtained subject to the two constraints. Hence we have the following formulation, which we shall call the dual problem. So there was an original problem which we can call the primal problem, and now we have another problem which is called the dual problem. Now these primal and dual, they are going to be equivalent in a sense, right? So constants for, already we have seen, just a minute. So let us go back, and therefore this is our equivalent problem. And by utilizing the resources, we should get rent, and these we have already seen. So those are the constraints. And see, therefore, this generalized term, we can say this, that if the primal problem is maximize z equal to cx subject to ax less than equal to b and x greater than equal to 0, then the dual problem would be minimize w equal to yb subject to ya greater than equal to c and y greater than equal to 0. So where A is in M into N matrix, B and X are column vectors and Y and C are row vectors. So this is in a vector form. Let us not worry too much about this formulation. We shall discuss this in our next class when we take up the duality theorems and further details. At that time, this can be understood in a much clearer manner. But let us now compare these two problems in a careful manner. So you see, this is our original problem and this is our dual problem. In the original problem, we have a problem of maximization. In the dual problem, we have a minimization. In the original problem, we have three constraints. All the constraints are less than equal to. In the dual problem, two constraints and all the constraints are greater than equal to. In the original problem, we have two non-negativity constraints, and in the dual problem, we have three non-negativity constraints. Now, if we look at the dual variables, then it will be very interesting thing will be revealed. What is that thing that is revealed? The dual variables, that is y1 and y2 and y3, they are actually connected to the constraints, right? So they are actually connected to the constraints, and those constraints are all greater than equal to 0. That is what we are seeing. And similarly, you will see that the non-negativity constraints of the primal problem or the original problem is connected to the constraints of the dual. In fact, for the time being, if you assume that x1 and x2 are the dual variables of this dual problem. So suppose now you want to take again dual of the dual. So you will find that these x1 and x2, which are the dual variables of the dual problem, their variable nature, that is whether they are equal to 0 or less than equal to 0 or greater than equal to 0, that would be determined by the constraint type. So between the primal and the dual problem, the constraints are connected to the variable type, and variable types are connected. So you see, let us put it this way, that this we call this primal constraints are connected to the dual variable type, and primal variable types are connected to the dual constraints, right? To understand these in a very simple form, if you simply think that if the original or the primal problem is in standard form of maximization, then the dual problem will be minimization in the standard form. All right, so that is very easy to understand. So what is the maximization standard form? The maximization standard form is, maximization as the objective function. All the constraints are less than equal to, and non-negativity constraints are all greater than equal to 0. So that is the standard form of maximization. So what is the minimization standard form? The objective function is minimization. All the constraints are greater than equal to, and the non-negativity constraints are all greater than equal to 0. So if you simply remember these two things, what are those two things? Number one, if the primal problem is in maximization standard form, then the dual problem will be minimization standard form. Right? This is one thing to remember. The second thing that should also be remembered is that if the, not if, the primal constraints are connected to the dual variable types, and primal variable types are connected to the dual constraints. Is it all right? So these are some of the things that we must remember so that our understanding of duality is very, very clear. Now, one more thing before we move over and try to see some more examples or some more insights. So look here, I have given you an example of product mix problem to a rent problem, and we have shown you how those two problems are, uh, paving the way towards formulation of the primal and the dual problem and show their equivalence. Now, you see, whether we should therefore solve the primal problem or we should solve the dual problem. It is not a very important thing. Whether you solve the primal problem or the dual problem, essentially you are solving the same problem. It is two ways of formulating the same problem. And therefore, both the problems should give the same solution. Please understand this. Because if these two problems are equal, irrespective of which problem you solve, the same solution must be obtained. That is one thing that you should remember, right? That whether you solve the primal problem or whether you should solve the dual problem, you must get the same solution. That is one thing. The second thing to remember is that, the primal problem, the interpretation of the primal problem and the interpretation of the dual problem, there should be a very, very clear rule that must be established. Please understand, all problems are not going to be your product mix problem, and all problems are not going to be your rent problem. The constants also need not be all less than equal to the original problem may not be in the standard form. If it is so, then how to find the dual problem? All right, so okay, we know that if it is in primal standard form, then the dual should be in other standard form. Or if one is maximization, the other one should be minimization. But beyond that, how do we find out? So let us first go step by step. As a first step, let us see if I have the primal problem, how can I write the dual problem? That's mechanically, without really going into interpretation and all that. What is the method? Let us see the method. So here is the primal problem. You take the three dual variables y1, y2, and y3, irrespective of whatever they interpret, with each constant, because I said that dual variables are connected with the primal constants. So here is the primal constants 4x1 plus 3x2 less than equal to 360. Now y1 is the dual variable associated with it. Y2 is the dual variable associated with the second constant, and y3 is the dual variable associated with the third constant. Now, what are the, your B values? B values means the RHS of each of these constants, right? So they are 360, 160, and 300. So it is the objective function of the dual problem should be 360 y1 plus 160 y2 plus 300 y3. Is it all right? So look here, that is written 360 y1, 160 y2, and 300 y3. Now, since the original problem is maximization, the dual problem should be minimization. If the original problem would have been minimization, the dual problem should be maximization. So you get the objective function. Now let us see how the constants are to be written. Now look here, these are the coefficients of x1. So if you multiply by the corresponding dual variables, that is 4y1 plus 2y2 plus 2y3 should be greater than equal to the profit coefficient of the original or the primal problem. So we get, you see, 4y1 plus 2y2 plus 2y3 greater than equal to 600. And for x2, 3y1 plus y2 plus 3y3 greater than equal to 400. Now question is, how do we know that it is greater than equal to? Is it because this is less than equal to, but then here are 3, here are 2? See, that is not how to see. What you have to see is look at the non-negativity constants. There are two non-negativity constants and both are greater than equal to. These actually are determining what should be the, the constant type of the dual problem. Is it all right? So if they are in standard form, they should be in standard form. So what is the standard form of maximization for the variables? They are all greater than equal to 0. So for x1, it is in the variable type is in standard form. So therefore, in the dual, the corresponding constant should be also in standard form. Is it clear? So you see, because x1 was greater than equal to 0, here the dual constant should be greater than equal to greater than equal to. Is it not? Why greater than equal to? Because this is standard form. This is also standard form for minimization. But supposing the original problem would have been minimization and constant type is greater than equal to 0 for variable x1, then the dual problem would have been maximization, and for maximization standard form for constant is less than equal to, then the same x1 equal to 0, here the constant type would have been less than equal to. So like these you have to understand very clearly, so that you can formulate the dual problem for the original problem, whatever the kind of problem that might have been given. Now let us see another very important concept, and that concept is dual of a dual is primal. So suppose we take the dual of the dual problem again, then what do we get? Look here, here is our dual problem. So what should be the dual variables? Let us say they are x1 and x2. So how do you take dual? Since the original problem is one of minimization, now this is our original problem. We are taking its dual. So if the original problem is is the dual problem, which we are taking dual again. In the dual problem, the objective function is minimization. So what should be the objective function of the dual of the dual? It should be one of maximization. All right. So now the dual problem is maximization. Now what should be the objective function? Objective function should be 600 x1 plus 400 x2, because these are the right hand side of the constraints and these are the dual variables. Should it be maximization or minimization? It should be maximization. Why? Because the original problem here, that is our dual problem, that is minimization. So the corresponding dual of the dual would be maximize z equal to 600 x1 plus 400 x2. Now what is the variable type? The variable type is y1 is greater than equal to 0, right? And the coefficients of the variable y1 is 4 and 3. So what should be the constant? 4x1 plus 3x2, connected to 360. Now what should be the constant type? See, look here, this is a minimization problem and the constant y1, the variable y1, the variable type is greater than equal to 0. This is in standard form. So the dual problem, which is now maximization, that also should be standard form in the constant type. So what should be the constant type? It should be less than equal to, right? So if you simply remember that if primal is in standard form, the dual should be also in standard form. If the primal is non-standard form, then dual should also be in non-standard form. And when you talk about standard form, you should understand maximization standard form or minimization standard form. And also constants are connected to the variable type, and for primal to dual, and from dual to primal also, the constants are connected to the variable type. So variable type to constants and constants to variable type. So therefore you see, if you take the dual of the dual problem once again, you get back the original problem. All right. So this is also another very important thing we should really look into. That is, the dual of the dual is primal, isn't it? So the dual of the dual is primal, that we have seen. Now let us solve the primal problem. So this we know very much clearly, that we can solve it by simplex. So if you solve it by simplex, then here is the formulation. We take 3 in the augmented problem. We take 3 more variables, which are slack variables. x3, x4, x5. They would be the basis in the first table, and the values will be the 360, 160, and 300. x3, x4, x5 would form an unity matrix, and the x1, x2 coefficients would be written. All right. So then we compute the Cj minus Zj. Cj minus Zj for x1 and x2. That should be uh, those that should be, in fact, this is not the final solution is directly shown, so we have not solved the problem. So here is our first table, because we have already solved this problem earlier, so we are not trying to solve this problem once again. We are simply showing the final solution. So this is our final solution. So the final solution really comes up to be x1 equal to 60 and x2 equal to 40. So the object, and x1 equal to 60 and x2 equal to 40, and Cj minus Zj values are all negative in the final solution. So that Z star is 52,000 that we have already seen. But interestingly, please observe the Cj minus Zj values of the simplex optimal table. Look here, they are called the absolute values of the Cj minus Zj in the final table. They are called the shadow prices. Right? They are called the shadow prices of the three different resources. So what are the shadow prices? The shadow prices are R1 equal to 100, R2 equal to 100, and R3 equal to 0. Because you see, this first, the slack variable x3 is connected to the shadow, to the resource, first resource. The x4 is connected to the second resource, and x3 is connected to the third resource. So if we say that three resources are R1, R2, and R3, then absolute value of Cj minus Zj's are 100, 100, and 0. So they are the shadow prices. So look at these shadow prices. Now let's look at the dual problem. So here is our dual problem. Minimize Z equal to 360 Y1 plus 160 Y2 plus 300 Y3, and subject to 4y1 plus 2y2 plus 2y3 greater than equal to 600, and 3y1 plus y2 plus 3y3 greater than equal to 400, and the non-negativity constants. So, we have already solved similar problems, or maybe the same problem, while discussing minimization problem. And that time we have taken a surplus variable and an artificial variable, and for both the constants, because it is greater than equal to type, and profit coefficients attached would be 0, 0, and m for the surplus variables, two surplus variables, and the two artificial variables respectively. So here is the simplex first table. In the simplex first table, you will see that because of the presence of the artificial variable, they should be 360 minus 7m, 160 minus 3m, and 300 minus 5m. So which variable y1 should be entering? Variable should be leaving 600 by 4 and 400 by 3. So a2 should be leaving. Now, anyhow, we can solve the problem, but here is the solution directly given, because these other details are available in previous classes. So here, if you look, again, you look at the final solution of the dual problem, you will now find the final solution is, y1 equal to 100, and this is wrongly written. This is not y5, this is y2. So y2 equal to 100. All right, so this is a mistake. It should be y2. So y1 is 100 and y2 equal to 100. So optimal solution is y1 star equal to 100 and y2 star equal to 100, and y3 is not in the basis, so value should be 0. So this is the optimal solution, and look here, what is the value of Z star? 360 into 100 plus 160 into 100 plus 0 into 300, so 52,000 again. All right. So carefully, observe that our primal solution was also 52,000 optimal solution, and in the dual also we are getting the same optimal solution. So I told you right in the beginning that the primal and the dual are two sides of the same coin. So whether you solve the primal problem or you solve the dual problem, you are going to get the same solution. Not only that, the shadow prices are also giving an indication of the original primal problem solution. So look here, when you are solving the dual problem, you are also solving the primal problem in a manner. So look here, your y4 and y5, which are your the two original surplus variables. Look, what is their Cj minus Zj values, absolute values, 60 and 40. These 60 and 40 are nothing but the primal solution. Let's go back to that primal solution once again. The primal solution was x1 star equal to 60 and x2 star equal to 40. Is it all right? And Z star was 52,000 and the shadow prices were 100, 100 and 0. And what is happening in the dual problem? In the dual problem, the solution is 100, 100 and 0 and the shadow prices are 60 and 40. So what has happened? We have got, the from primal we can get the dual solution. From the dual we can get the primal solution. There is no surprise here because dual of the dual is primal. So if one is primal, the other one is dual, right? So you sometimes they are called primal dual pair, right? So they are called primal dual pair. Why they are pair? Because if we take dual of the primal, we get the dual problem. If we take the dual of the dual, we get the primal problem. So whatever is true in the relationship between primal to dual, that is same thing is also going to be true for dual to the primal. Is it all right? So this is in a way, the relationship is on both sides. So if you again compare the original and the dual solutions, so once again to bolster what we have found in the primal problem or the original problem, the optimal solution is x1 star equal to 60, x2 star equal to 40 and z star equal to 52,000. And the shadow prices of the three resources are 100, 100 and 0. And in the dual, the optimal solution is y star 1 star equal to 100, y2 star equal to 100 and y3 star equal to 0 and z star equal to 52,000. Shadow prices of the two resources are 60 and 40. Look here, these shadow prices are the primal solution and these optimal solution of the dual are shadow prices of the primal. And both ways the relationship is true. That means the shadow prices of one is the optimal solution of the other. Is it all right? So that means the shadow prices are nothing but solutions of the dual problem. Is it not? Now you see, suppose there is a problem, that primal problem is difficult to solve. You can convert it to dual and you can solve the dual, and from the shadow prices you can get the solution of the primal. Is it all right? So these are some of the very, very interesting thing that you can observe when you take the dual. But the duality is not about just making another formulation and making some solutions. The duality can really help us in very, very important, interpretations of the simplex problem. Not only that, there are many other applications. For example, in the transportation problem, you might have heard about UI and VJ, the Modi methods. Those are nothing but those UIs and VJs which are useful in transportation problem for calculation of Cij minus Zij values. They are nothing but the dual solutions of the original transportation problems. Is it all right? In network related problems, which we shall see much later, there also the duality gives a very, very important interpretations which help in solving networks problems, right? So duality is very useful and it can help in many different ways. There are some very specific interesting duality problems which can be solved without even solving by simplex. Just by forming the dual and interpreting the primal and the dual, we can make very, very good interpretations. There is also another very interesting finding which is called the complementary slackness condition. What is complementary slackness condition we shall discuss in great detail in our subsequent classes. But here, let me only tell one thing. You see, the solution of y1 is equal to 100. Now, y1 is the dual variable for the first constraint. Now, if you put the optimal solution of the primal problem, that is x1 equal to 60 and x2 equal to 40, in the first constraint, what do you find? That 4 into 60 plus 3 into 40. 4 into 60 is 240, 3 into 40 is 120. So 240 into 120 plus 120 equal to 360. So that means at the optimal point, the first constraint has turned to equality. In another language, you can say that the slack of the primal first constraint has vanished, right? So the complementary slackness says that if the dual variable exists, that means if the dual variable has a value in the optimal solution, say for example, y1 has a value that is it is 100, then the corresponding primal slack will vanish in the optimal table and the corresponding primal constraint will turn to equality. Is it all right? Same thing you will see at y2 equal to 100. So the dual variable, that exists, right? It has a value. So what would happen to the primal slack in the second constraint? Again, put 60 and 40, 60 into 2, 120 plus 40, 160. Look here at the optimal table, the second constant has also turned to equality. Is it all right? So that is complementary slackness. But in the third constraint, y3 does not exist because its value is 0. But if you put 60, 40 there, what do you get? 120 plus 120, 240. It's not equal to 300, is it not? So because y3 does not exist, there is a value of 0 out there. Its slack has not vanished. All right. Same thing in the look here, the x1 equal to 60 and x2 equal to 40. If you go for primal to dual, now if you put 60 and 40 and the shadow prices, that is 100, 100 and 0. All right. So look here now, corresponding to x1, x1 is 60. So there is the primal variable x1 that has a value. Now what happens to the dual constant then? You put 100 and 100, you get 400 plus 200, 600. Since x1, the dual of the dual constant x1, which is the primal, x1 exists, it has turned to equality. About x2 also, let us see. See, x2 was 100. X2 here exists, it is 40. Now, if I put your optimal solution, that is 100, 100 and 0 in the second constraint, again you get 3 into 100, 300 plus 100, 400 plus 0. So 400. So that means the second constraint has also turned to equality. In fact, both the constants have turned to equality because both the primal variable exists. They have certain value, that is 60 and 40 in the optimal solution. So this is complementary slackness. If the the correspondingly either primal or the dual in the optimal solution has a value, then the corresponding primal slack would vanish in the optimal table, or the dual slack would vanish in the optimal table, and the constant would turn to equality. Now that complementary slackness condition is used again in various problems for various interpretations. All right, so the primal and dual problems are both formulations of the real problem. Which one is a better formulation is decided by the context of the problem. The dual formulation helps in obtaining better insight of the problem at hand. More will be discussed in the subsequent classes. So I already told that we shall discuss other theorems. We shall see many examples and things of that sort. The shadow prices are nothing but the dual solutions. In that sense, the shadow prices of the dual problem are the primal solutions that we have already seen in the example. All right, and dual of a dual is the primal. So these are some insights on duality. This is so important that let me read out once again. The primal and dual, they are both formulations of the real problem, and which one is the better formulation is to be decided. The dual formulation helps in obtaining better insights. More will be discussed later. The shadow prices are nothing but the dual solutions. In that sense, the shadow prices of the dual problem are the primal solutions. And finally, dual of the dual is the primal, right? Now, the dual problem is connected to the primal problem in an unique way. The variable type of the primal problem decides the type of the dual constraints. The constant type of the primal problem decides the variable types of the dual problem. So look here, constraints are connected to the variable type of the dual, and the variable types are connected to the constant type of the dual. So that should be remembered. By the same coin, the variable type of the dual problem decides the type of the primal constraints, and the constant type of the dual problem decides the variable type of the primal problem. Then dual of a dual is primal. So this is the original problem, this is the dual problem, and we have already seen that if you take the dual of the dual, you get back the primal. All right, so this already we have seen. That slide is shown again to bolster our ideas. Now, here is a very good summary of what we are trying to say in a tabular form. So if the primal problem objective function is maximization, then in the dual, the objective function should be minimization. In the primal problem, if the constant type is less than equal to, in maximization problem, that is very important. So they are not independent. All the three things are connected to one another. Right? They are all connected. That must be remembered. How it is connected? Look here. The constant type is less than equal to in a maximization problem. Right? The variable type should be greater than equal to 0. And if the variable type is greater than equal to 0, then constant type is less than equal to. Now you see, only when this is true, when the primal is maximization standard form, dual should be minimization standard form. All right. So also note that the dual constant type is greater than equal to minimization standard form because the primal variable type is greater than equal to. Right. So now here is the other formulation, is a more general formulation. So they are in non-standard form. Suppose the primal is maximization and the constant type is equal to, then dual variable will be unrestricted in sign in a minimization problem. If the primal constant is greater than equal to, the dual problem would be less than equal to 0 in a minimization problem. And in the variable type, if the variable type is greater than equal to 0 in a maximization problem, the dual constant type would be greater than equal to. And if the primal has unrestricted in sign variable type, then it should be not 0, it should be equal to. It is mistake, it is written 0, it should be equal to. If the variable type is less than equal to 0, it should be less than equal to in a minimization problem. So anyhow, you don't have to really remember all these details. You can simply remember everything by a simple rule that if it is standard form or maximization, the other one will be minimization standard form. And whenever it will deviate in the primal, it will deviate in the dual also. So now you see, this is now the other part, that is if the primal is in minimization. So here is the primal minimization and the dual maximization. So what happens if it is less than equal to, then the variable type should be less than equal to. Why? Because in minimization standard form is greater than equal to. That should be the dual maximization standard form of variable type that is greater than equal to 0. So these are connected. All right, and rest is for equal to, it should be unrestricted in sign, and for less than equal to, because for minimization problem less than equal to is non-standard. So variable type should be non-standard also. And if the variable type is greater than equal to 0, which is standard, then the constant type should be less than equal to because it is maximization. That is the standard form. If it is unrestricted in sign, this should be equal to 0 is written by mistake. And if it is less than equal to 0, then it should be greater than equal to. Because for maximization, uh, less than equal to 0 for minimization in the primal is not standard. So therefore, in the dual problem, which is of maximization, the constant type should be non-standard also, that is greater than equal to. Anyhow, all these rules are applicable. Let us look at a very simple example problem. So in this example problem, find the dual of the following problem. Maximize z equal to x1 plus 2x2 minus x3 subject to 2x1 plus x2 minus 3x3 less than equal to 15 minus 4x1 minus x2 plus x3 less than equal to 12 and x1 plus 3x2 less than equal to 20. x1, x2, x3 are unrestricted in sign. All right. Let us say the three dual variables are y1, y2, and y3. Now, the primal problem is one of maximization. So the dual problem should be what? It should be minimization. What would be the function? It should be then 15y1 plus 12y2 plus 20y3. Is it not? So 15y1 plus 12y2 plus 20y3 should be the objective function. That is the first thing. Now what should be the constants? 2y1 minus 4y2 plus y3. Now it should be what? It's connected to 1. In which way? Look here, the first constant is related to the variable type. So what is the variable type? x1, x2, x3, all the variable types are unrestricted in sign. So therefore, all the constants in the dual should be equal to. That means the three constants would be 2y1 minus 4y2 plus y3 equal to 1. Then y1 minus y2 plus 3y3 equal to 2. And minus 3y1 plus y2, nothing because no x3, equal to minus 1. All right. So that must be remembered. Now what would be the variable types of y1, y2, y3? That is connected to the primal constants. Now it's a maximization is the primal problem. The standard form is less than equal to. So the primal constants are all in standard form. So that means the dual variables should also be all in standard form. That means y1 greater than equal to 0, y2 greater than equal to 0, and y3 greater than equal to 0. So precisely that is what has been done here. So look here, these are 15y1 plus 12y2 plus 20y3, that is minimized because it was maximized. Because it was all unrestricted in sign, all the constants are equal to, is it not? And thirdly, because it's a maximization problem in primal and the constant types are all in standard form because less than equal to, therefore all the three variables in the dual should be greater than equal to 0. All right. So you are now confident about formulating, dual problems for any kind of primal problem. If it is maximization standard form, dual will be in minimization standard form. If the primal is minimization standard form, the dual will be maximization standard form. If the primal is in non-standard form, then you have to check for every constant and every variable. Every constant, if where the standard form is deviated, the corresponding variable type would be of that deviation. And same thing about the primal variable type to the dual constants. So if you remember this, then you can make any formulation without any difficulty. So here another example. It's a maximization problem and subject to three constants. And you can see that x1, x2, x3, they are all greater than equal to 0. So one thing is clear that if we have to find its dual, if the original problem is one of maximization, dual should be one of minimization. So there is no problem there. Now the constant types. What should be the constant types? Because each of the variable are in standard form of maximization. That is, all are greater than equal to 0. So since the dual is minimization, each constant should be also in minimization standard form. What is the constant type of minimization standard form greater than equal to? That means all constraints in the dual should be greater than equal to type, right? Now, because the primal constants types are different, in the dual, the variable types will be different. The first one is equal to. So the corresponding dual variable y1 should be unrestricted in sign. The second constant is greater than equal to. Now greater than equal to is in non-standard for maximization problem. So therefore in the dual, y2 should be less than equal to 0. And finally, the third constant of which the y3 is the dual variable, maximize, that's the primal problem, and the constant type is less than equal to, which is in standard form. So therefore the dual variable y3 should also be in standard form. That means y3 should be greater than equal to 0. So here is the solution. See, the original problem is maximization. The dual should be minimization. The variable type x1 is greater than equal to 0. So first constraint should be greater than equal to. Why greater than equal to? Because this is the minimization and this is in minimization standard form. Is it all right? So therefore, for minimization standard form, it should be greater than equal to. And all the constraints are, like that. And therefore, they should be in that format. So no problem there. Only problem is that since it is equal to, then y1 should be unrestricted in sign. Since it is greater than equal to, which is non-standard for maximization, y2 should be less than equal to 0. And in the third constraint, since it is less than equal to, which is the maximization standard form, then it should be greater than equal to 0. That is for y3. That is the third variable. Right. So in this particular lecture, I have discussed about duality, the basic idea of duality, how the primal and dual problems are equivalent, how a dual of a dual is the primal, how shadow prices are connected to the dual solutions, how to convert a primal problem to the dual problem, how variable types are connected to the constant type of the dual, and constant types of the primal are connected to the variable type of the dual, how standard forms of the primal correspond to the standard form of the dual, whether it is maximization standard form or the minimization standard form. I have also very briefly introduced the complementary slackness idea, right? The complementary slackness is a very, very important concept in the idea of duality, and that we shall take up in a very big way in the subsequent classes, and also the various duality theorems, right? So with that, I stop here, and therefore thank you very much for patiently hearing, and we shall continue from this point in our next class.